Hi everyone, and welcome to my YouTube channel. Every time I read a research paper, I plan to create a review video and break down the concepts for everyone interested in AI. But I never got round to recording this video. Finally, I'm getting round to doing it. Okay, today we are going to check out an academic paper from OpenAI. As you know, OpenAI is a pioneer in the field of artificial intelligence. And this paper from 2022 is definitely worth reading, considering that OpenAI is a leader in reinforcement learning. Here is the first slide. As you can see, there's a title of the paper and the names of all authors. The authors indicated by a star next to their name is the primary author. Okay, this is the abstract of the paper. And this paper is the exact moment that the industry realized that the bigger wasn't always better. And this paper admitted in the first paragraph. And our main question in this paper is, how can we steer a gigantic model like GPT-3, which can be unpredictable, to align with humans and respond trustfully and helpfully? And as you know, the trustfulness problem is crucial. And I think I used the wrong vocabulary. Trustworthiness problem is crucial. For example, suppose a company uses AI for screening resume to choose the ones with sufficient skills, but maybe the model is biased and prioritize a specific gender for a specific job. For instance, if the job is mechanic, the model might favor men. And as you know, this bias could ruin the screening process. Okay. And we have a key term here, misalignment, align. And this paper is, trying to making language model align with humans. And in simple term, alignment means to matching AI goals with your goals. Okay, let's answer to the question in this slide. Why are language models always helpful? It's simple because the core problem is a mismatch, a misalignment between the next token prediction training goal and what user actually wants. These models are trained to predict the next token, not to align with the user, and this leads to undesired behavior such as generating fake facts or you know hallucinating fake facts. I remember when I asked GPT-3 about a striped hyena in Persian, I asked this question in Persian, in Farsi. What is striped hyena? And it claimed that it is striped hyena is a food in Khorasan province in Iran. And it's not a food, it's an animal. And the model simply lacked the perception to understand the difference. And then there's a bias problem I explained in the previous slide, and simply failing to follow constraints. For instance, if you ask it to write a sentence in 200 hours, in 200 words, sorry, it might not adhere to the limit. Okay, you might ask yourself, how can we measure alignment? Since alignment is an abstract concept, how can we evaluate it? Well, this paper introduced three main alignment criteria: helpful, honest, and harmless. First, helpful, well, which is self-explanatory, means the model should assist user in solving their tasks. Second, honest, and means it shouldn't fabricate information like the example I mentioned earlier. And third, harmless, means it cause no physical, psychological, or social harm. And these concepts are pretty straightforward. Okay, the essence of this paper is spelled out in this slide. This paper focuses on fine-tuning using RLHF in 3 steps. RLHF stands for Reinforcement Learning from Human Feedback. So let's break down each step one by one. Let's go through the first step. Okay, at first step, they hire 40 contractors and ask them to write desired demonstration for various prompts, desired response. They take a sample from the prompt dataset, for example, explain the moon landing to a 6 years old and give it to a labeler. The labeler then writes a high quality response for that prompt. Finally, they use this data to fine-tune GPT-3. We call this model SFT. SFT stands for Supervised Fine-Tuning. As you can see, the blue arrow indicates that we are using this data to fine-tuning the following model. And we use this data to fine-tuning SFT model. Okay, maybe you're asking yourself, how can we scale this? We can't manually write desired response for every prompt in the universe. So how do we continue this process? How can we continue? Okay, step 2 solve this. In step 2, contractors wrote response by hand. Sorry, in step 1, contractors wrote response by hand. But in step 2, we give the prompt to the model. It generates multiple responses. And then we give those to the labeler. Instead of writing desired response, the labeler ranks the model's output. For example, A is better than C, C is better than B, and we continue this process. Then we use this ranking data to train a reward model. As you can see, here is the blue arrow. We use this ranking data to train a reward model, and now we have a reward model. This model learns what humans prefer. It predicts human judgments and recognizes human preferences. Okay, now we have two models, SFT model, Supervised Fine-Tune model, and RM, Reward model. Now, in step 3, uses reinforcement learning to train our final model. Here is the loop. We sample a prompt from dataset, give it to the model, and model generate a response. Now, we feed this response to reward model, and reward model outputs a score, not a ranking. Reward model outputs a score. And now we use that score to train SFT via PPO. As you can see, here is the blue arrow, and we use this data, this ranking data, to the model. And model learns to maximize score. And here is the magic. The final model, called PPO, generate output that gets high scores from the reward model. And this is the essence of the paper. Okay, let's deep dive into step 1. In the first step, we train an SFT model using supervised fine-tuning. We provide a dataset of prompt response example, about 13,000 prompts, where each prompt has a human written desired output. We fine-tune the model so that when it sees a similar prompt, it generates a similar answer. The result of this step is the SFT model. In step 2, they train the reward model, a dataset containing human rankings for about 33,000 prompts, is used to train the reward model to predict human judgment, human preferences. For each prompt, responses are provided, resulting in chi-squared comparisons in total. And to prevent overfitting, they train all chi-squared comparisons per prompt at single batch. For more in-depth details on these training steps, you have to check out the original paper. This is just the review video. Now let's examine the loss function for the reward model training step. At first glance, it appears complicated, but it's actually straightforward. Let me explain. Our reward model here, denoted as R sub theta, it takes two parameters, prompt, which represents by X, and response, which represents by Y. Now, YW here is the preferred response and YL the less preferred response. The model trained such that the score for the preferred response, this, is higher than the score for less preferred response, this. So now the difference between these scores is then passed through a sigmoid function and subsequently a log function. Go to the sigmoid and then pass through the log function. Now, finally, we calculate the expected value across all comparisons in the dataset here and multiply it by constant. This is our constant, and I explained K in the previous slide. And now we use this as the loss, which is then backpropagated. Here is an example to help clarify the previous loss function, which may look complicated at first. Suppose we have a prompt, let's call it X, summarize this article about climate change. Now we have two responses that were ranked by human labelers. As I mentioned earlier, this step uses a human ranking dataset. Let's say YW is the preferred response. For example, the article states rising CO2 levels cause global warming. And the reward model might assign this response a score of 5.0. And YL is the less preferred response. For example, the article claims climate change is a hoax, and the reward model score for this response might be 2.0. Please note that these responses are just illustrative examples, and the actual output reward model could be different. Okay, since we have two responses, K is equal to 2. And we have two responses, so we have one comparisons. Okay, let's walk through the calculation step by step. First, we find the difference between the rewards assigned to the preferred response and the less preferred response. In our example, this is 5 minus 2, which equals 3. Next, we apply the sigmoid function to this reward difference. The sigmoid function helps convert the raw reward difference into a probability-like value. It maps any value to between 0 and 1. Okay, we then take the natural logarithm of the sigmoid's output. Then the next step involves calculating the expected value. Since we only have one comparison in this specific example, the expected value is simply the value we just calculated. If there were multiple comparisons, we would average the log results across all of them. Okay. Finally, the loss for the reward model is the negative of this expected value. This is common practice to turn a maximization problem into a minimization problem. Okay, this gives us our final loss value for this particular comparison. Now, let's move to the third step, the reinforcement learning group. This is where we refine our language model using the reward model we've just discussed. We began by using the reward model to guide the optimization of our SFT model. SFT stands for supervised fine-tune, and this is the result of the third step, the first step we've just discussed. Essentially, the reward model provides feedback on how well SFT models align with the user, how well models output align with desired characteristics like helpfulness and harmlessness. Initially, we train a PPO model. PPO stands for Proximal Policy Optimization. However, we often find that this first PPO model might not be perfectly aligned with our goals, especially for simpler NLP tasks. And to address this misalignment, we introduce a refined approach, often referred to PPO PTX model. This is the new result model. And this method strategically mixes the reinforcement learning update from PPO with pre-training gradients. And InstructGPT is the culmination of this RLHF process. And we have our InstructGPT with 1.3 billion, 6 billion, and 175 billion parameters. And these models are significantly better at understanding and responding to user prompts in helpful, honest, and harmlessness manners, thanks to reinforcement learning. Now, let's move on the results on API prompt distribution. InstructGPT with 1.3 billion parameters is significantly better than GPT-3 with 175 billion parameters in terms of efficiency. With 100 fewer parameters, it achieves an 85% win rate against GPT-3. However, they were not satisfied with this result, so they also checked generalization. They used held-out labelers. Labelers who did not work in the training step. In training step, they used 40 contractors, as I mentioned earlier, and the held-out labelers were people who were not from those 40 contractors. They found that 77% of these human labelers preferred this new InstructGPT. And this showed that the model did not overfit to the training labelers. Okay, this is the results we've just discussed. As you can see, the PPO and PTX model with 1.3 billion parameters are outperformed GPT-3 with 175 billion parameters. And they used an SFT model as the base model and compared other models against it. Okay, on the next slide, you can see the results for three more metrics. As you can see, InstructGPT is better in user assistance. It also excels at explicitly following constraints. Furthermore, in terms of hallucination, it is much better than GPT-3. However, in hallucination, SFT model is better than PPO and PPO-PTX models. Okay, here are the results for NLP tasks using the FLAN and 2 dataset. And FLAN and 2 is the public NLP dataset. You can find it in Appendix and in Appendix C from the original paper. Okay, when GPT-3 was fine-tuned with these datasets, we compare it with InstructGPT. The results show that InstructGPT achieved a 78% win rate against GPT fine-tuned with FLAN, and also it's achieved 79% win rate against GPT fine-tuned with 2 datasets. And you might wonder why this happened. Even though we fine-tuned the model with these datasets, another model trained using RLHF performed better. Why? Because the model trained solely on the datasets didn't learn to align with the user's intent. Okay, on this slide, you can see the results for trustfulness. In the Trustful QA benchmark, I'll show you this dataset in the next slide. InstructGPT generates trustful and informative answers that are twice as good as GPT-3's. There's one exception. PPO-PTX model with 1.53 billion parameters performs slightly worse and, as you can see, matches GPT-3. Okay. Trustful QA is a benchmark dataset designed to test whether AI models can answer questions trustfully, especially questions where common misconception exists, common myths exist. It checks whether the model can resist false but popular beliefs, stay factual, and only answer when it's sure. By comparing how often different models answer correctly, researchers can see which one are better at staying trustful. Now, in this slide, you can see the results for toxicity. They found that InstructGPT generated 25% fewer toxic output when prompted to be respectful. However, there's a limitation here. If you ask InstructGPT to become more toxic, then it becomes more toxic than GPT-3 because it learned to align with human intentions. So if a human asks it to become more toxic, it says, yes, sir, and become more toxic. Okay, let me point out a limitation. They found that this RLHF process doesn't improve biases, and the model still has biases. They used the binogender dataset to test for biases, but it doesn't perform well. And I think it's obvious because reinforcement learning from human feedback, it relies on human input, and humans' input have inherent bias. So the model inherently learns those bias. Also, they checked out of distribution generalization. They prompted the model with French, and InstructGPT wrote the answer in French, but GPT-3 ignored the language and wrote in English. There were also, coding problem, and InstructGPT explained the code logic, but GPT-3 just guessed the option. And, it's a breakthrough. It shows that alignment methods can generalize beyond the training data. However, InstructGPT still has common mistakes. For example, it accepts false premises. For instance, when asked why it sucks after meditating, it accepts the premises and explains why sucks are important. It doesn't recognize it's a nonsensical question, It takes it seriously instead of recognize it's absurd. Also, it goes over its head. For example, when prompted, what happened if Knoonball hit pumpkins? The answer is obvious. The pumpkin explodes, but InstructGPT overthinks it, and it lacks the perception to understand simple scenario. And that's the end. Thanks for your watching. If you found it interesting, please share it with your friends, and goodbye and see you in the next video.